Hey folks, so this is a promised video for Calc A students on the Fundamental Theorem of Calculus. So just to remember, the Fundamental Theorem of Calculus has two parts. It says if f is continuous on a closed interval AB, then the first part, the derivative of the integral from a to x of f of t dt equals f of x. And we said this was the intuition that let us understand that the derivative and the integral are sort of opposites, right? And part two said, well, if I wanted to calculate a definite integral, the integral from a to b of f of x dx, then this would equal capital F of b minus capital F of a, where capital F is any antiderivative of the integrand little f. So what I promised you was a video on understanding, in particular, part one of the fundamental theorem. So what we will want to do is remember that we're thinking about this function little g, which is just the thing inside the derivative here, right? Little g is the integral from a to x of f of t dt. And so what little g is measuring, remember, is the area under the curve from a up to x of my function f, right? So g is really the function that measures area. Okay, so this area is g of x, okay? For different x values, you get different areas, fine. So the goal of part one of the fundamental theorem is to say that function g, this integral, if I were to take the derivative of this with respect to x, I would get back little f. So that means what I want to show is the derivative of g is little f. So how do I calculate the derivative of this little g? Well, what I want to do is go back to the limit definition of derivative. So let's recall g prime of x is, by definition, the limit as h approaches 0 of g of x plus h minus g of x all over h. This is for any function, right? The definition of the derivative. So let me go ahead and plug in, right, the actual definition of g, right? So g of x plus h means I'm integrating from a up to x plus h. So let me write that down. Integral a to x plus h g, sorry, not g, f of t dt. That's my g of x plus h. So let me go ahead and just underline this and this to remember that these came from the same place, minus g of x, so that is the integral from a to x now, f of t dt. And again, let me underline this maybe with a different color. G of x is now this, okay? Just so I remember where it came from. And remember, all of this is divided by h. Okay, so far so good. Now, maybe what you are wondering is how do I make any progress from here? Well, what I notice is that I have the difference of two integrals, and I have a lot of rules that let me manipulate and combine integrals. So let me recall some of those properties. So this whole thing equals the limit as h approaches 0. So the first integral I'm going to leave alone. But the second integral, I'm going to swap the x and the a bounds. And remember, one of the properties we said is that if you swap the bounds of an integral, you have to add a minus sign. So this is already a minus integral. So I'm going to say this is the same as plus the integral from x to a, f of t dt, all over h. Okay. But now I see I have an integral, and maybe it's actually easier to think about reversing these two integrals. So I'll think first about the integral from x up to a, and then I'm adding the integral from a up to x plus h. But this is another property that we know from integrals, that if I have two integrals and the bounds, you know, of the top of one is the same as the bottom of the other, right? I'm allowed to combine these into one big integral. So this is the same as the limit as h approaches 0 as the integral from, so now I'm going x up to x plus h, f of t dt, all over h. Okay, again, this is one of those properties of integration, right? X up to a plus a up to x plus h. Sort of these a's are the same, which means I can combine these into one integral now from x up to x plus h. Okay, so now at this point, right, there's not much more simplification we can do. So what I'd like to do is really, let's draw a picture to kind of understand what we're looking at. Okay, in particular, what does this numerator represent? Okay, so this integral from, from x up to x plus h. So if I were to again draw my picture of f, looks something like this. So now remember, I have an x here and maybe an x plus h, which is just next to it. Okay, we know that h is going to eventually go to 0, so we can think about h being a really small number. So this integral is asking what's the area under this curve, under this little curve segment. And I guess what's interesting that I notice is that, well, x and x plus h are maybe very, very close to each other. And so the closer they are together, sort of the skinnier this little rectangle becomes, right? And so I'm going to make an observation. And this is the one moment of this explanation, which is no longer rigorous, but at least will help us understand why this is still, this result is still true. So what I notice is that because the interval x up to x plus h is so small that f of t on this interval is essentially constant. What do I mean by that? So in this picture, you might look at this and say, well, no, this function f isn't completely constant on this interval. No, I agree. It's not completely constant. It definitely goes up and down. But if h were super duper small, right, then the amount that this function f can vary is really tiny, right? It can't go up and down that much in a tiny, tiny interval. And in fact, the smaller I make the interval, the less I expect f can go up and down. So in other words, what I'm saying is f of t is roughly equal to, let's just say, f of x, no matter the t value, right? And again, what I mean here by f of x is really a different color, the value at the left end point here, right? So this f of x. And so what I'm saying is, give me any f of t in this interval. Maybe this is my f of t. And if the interval's super duper tiny, f of t and f of x must be pretty similar, right? The left endpoint's a pretty good approximation of the entire function on this whole interval, okay? So this is somewhat intuitive, but it can be made rigorous. So then let me say that what I've written before is approximately then equal to the limit as h approaches 0 of, so the integral from x up to x plus h, f of x dt, all over h. And now the thing that we have to remember is that this integral is in terms of t, right? I'm asking to go from, different values of t, but really I am fixing f of x, right? F of x is now just a constant. Which means I can pull it out, right? It doesn't depend on t, which means I can pull it out. So if I pull it out of the integral, I have f of x times the integral from x up to x plus h of 1 dt, all over h. And fortunately for us, there is a wonderful formula for the integral over an interval of a constant. So this is f of x times, this is 1 times x plus h minus x. Ooh, too many brackets, okay. Okay, where here, I've used the fact that the integral of a constant is truly just the area of a rectangle. So this is height 1 rectangle with width x plus h minus x. Okay. And now we've just made it to the end. This shows us the limit as h approaches 0, f of x times, now what's left over here, the 1 of course goes away, x plus h minus x is just h again, divided by h. I now have cancellation of the h's. This is the limit as h approaches 0 of f of x, which of course there's no h's anymore to even worry about. I can evaluate the limit by just getting rid of the limit. I'm left with f of x. And where did this, start from? Remember, way back when, we started from what is the derivative of g. So we have successfully shown that the derivative of g is truly little f. Okay, so this is a really interesting example because I think it really ties together a lot of intuition and ideas from different sections of the textbook. It's really having us remember what is the definition of derivative, what are properties of integrals, and this little step in the middle where I said, well, we're going to approximate everything by the left-hand point. Maybe it gives you memories of Riemann sums, right, that we did in section 5.1. What's very interesting is to make this even more rigorous, you can use other theory that we've also talked about this semester, but I'll leave that as a mystery for now. Okay, so I hope this was interesting and insightful. If you have any questions about the fundamental theorem of calculus, please don't hesitate to ask, and I'll see you in class.